This is Bharat Kumar and Sugantraj from Department of Chemical Engineering, Railtech High-Tech. Our project is based on simulation of fractionating column in petrochemical industry using Aspen Hysys. The operating conditions of distillation column can influence both product quality and energy efficiency of the process. An isobutene fractionating column at Kothari Petrochemicals was simulated using Hysys simulator. The shortcut column was A shortcut column was simulated to predict the optimum operating conditions. Then another fractionating column was simulated with the optimized operating conditions obtained for the same product purity. Then economic analyzer in Hysys evaluated the cost of the optimized fractionating column. The cost of the optimum column was compared with the cost of actual fractionating column. The profitability was studied. Procedure: the fractionating column in the feed preparation unit of Kothari Petrochemical was taken as the case study. The LPG feed from the nearby refinery is fed to the distillation units for subsequent separation of isobutene from C3, C4 and C5 compounds. If any design changes for the column is to be adopted for better performance and economics, it cannot be built readily. Evaluation of such design changes have been made possible by process simulation softwares like Aspen Hysys, Aspen Plus, and etc. A fractionation column was used to recover isobutene as top product with high purity. The real operating conditions of the column obtained from the plant are shown in table 1. The feed is a LPG bought from nearby refinery, which is a multi-component mixture containing 0.16% purity of isobutene. This is the flowchart for the feed preparation unit in Kothari Petrochemicals. These industrial data were regenerated in the simulation environment. The results of simulation were found to be synonymous with actual plant results and only with negligible deviations. The simulation of fractionating column was done using Hysys simulator. The fluid package used was Peng Robinson, since it is a widely used refinery simulation software. The selected method for simulation of the ISIM inside out. The shortcut method was used to predict the optimal feed stage, actual number of days, and the reflux ratio for distillation column. The shortcut method requires identification of the light and heavy key components from a multi-component mixture. The component with least mole fraction in distillate was the heavy key in distillate, while the component with least mole fraction in bottom was the light key in bottoms. From the Table 3 shows the design basis for simulation, and Table 1 represents the real operating conditions of the fractionating column. Figure 2 and Figure 3 represents the shortcut column parameters and the shortcut column performance respectively. Results: the optimum column operating conditions obtained from the shortcut method was applied in simulation environment to test the performance. Another fractionating column was simulated with these optimum parameters for the same percentage of top product fractional recovery of isobutenes as 99.65% as in the actual industrial column. The feed conditions remain the same. The parameters varied from the actual data are shown in table 4. The optimization of these selected operating parameters affected the energy efficiency rarely. The energy requirements of reboiler and condenser decreased slightly as the number of trays was decreased from 100 trays to 64 trays as shown in table 5. The composition of the distillate of the fractionating column with modified operating conditions was compared with the top product composition of actual industrial column as shown in table 6. So we can infer that the effect of this change only had a negligible effect on product purity and energy efficiency. The simulation model developed for isobutene fractionating column was verified against the real plant data to test the suitability of the parameters obtained from the shortcut method. Valid conclusions were arrived after comparison of simulation results and actual plant data. These are the table 4 and 5 which was previously. Aspen process economic analyzer in Hysys evaluated the cost of the optimized fractionating column. The cost factor is the cost spent in production for every kilogram of material stream. For example, cost of feed per kilogram or cost of product per kilogram. These data were collected from the industry and the cost factor was found to be 0.3 for the feed and 0.26 for the product streams in terms of mass flow. Table 7 represents the cost factor of material streams and figure 4 represents the material stream summary grid with cost. Our study is only in respect with the effect of column conditions on operating cost. Other capital costs were not considered. Figure 6 represents the economic evaluation summary for the actual industrial column. Figure 7 shows the economic summary of the optimized column. The number of trays was reduced from 100 to 64 and the operating cost also decreased simultaneously from $20.4 million per year to $19.9 million per year. The percentage profit was found to be 2.51% of the overall operating cost. The main operating conditions that affected the operating cost was found to be the change in number of trays Figure 8 represents the operating cost versus number of trays plot, which clearly depicts the fall in operating cost as number of trays decreased. Figure 6 shows the economic evaluation summary of a column with real operating data, and figure 7 shows the economic evaluation summary of the optimized distillation column. Figure 8 represents the plot of operating cost versus number of trays. Conclusion: the result of this study indicates that the optimization of operating parameters like number of trays, feed tray location of the fractionating column played a vital role in improving the cost efficiency of the unit. Besides maintaining the same top product purity, the reboiler and condenser duty slightly increased as the number of trays decreased, but the cost efficiency improved. The operation of the distillation column is optimized for achieving balance between operating conditions and operating costs. The most reasonable operating condition change was the reduction of number of trays. This change had a significant effect on product purity and energy efficiency, and simultaneously this change has reduced the overall cost. The number of trays was reduced from 100 to 64, and the operating cost also decreased simultaneously from 20.4 million US dollars per year to 19.9 million US dollars per year. The profitability percentage was found to be 2.51% of the overall operating cost. Primary attention must be given to the operating condition that can improve the savings. This is the outcome of this case study.